wouldn't give a talk like that, and I think it was very interesting. Very good, and maybe gives you a different perspective. And I'm going to give, so we're going to talk a bit more, you can say modern, even though the research stream, which I'll mention a little bit, it's from 2003, which now is almost 20 years old. But also I'll talk a little bit, I was asked to talk a little bit about work that was done by Kevin and Natalie, and Kevin, right, and some other papers have been working on some interactions with field theory, and that gives a little bit of a good perspective on these things. And, but I'll try to go very slow. I won't go into too much detail unless I'm asked, but please do ask, and I can give some more details about things. So it can be a bit more of a informal talk. Okay, so let's go next. A little bit of recap from yesterday. Mr. Space. So, Mr. Space, which are usually denoted projective Mr. Space. As David explained, you can see it as an open subset of tree where you take out a line which corresponds to this line in infinity. You can also see that as being the total space of
so the projective space is 6-dimensional, and then non-projective space is higher dimensional than that.
yeah,
I must have worked this 10 times. Sorry.
yeah, you can take there's a scaling that you take out to get to CP3. Right. Usually, when you talk about projective, when you talk about Fisher space, it usually just means this projective Fisher space. You might see some other references talk about Fisher space, but the scaling is not taken out. But always taking out the scaling, and this is what I mean by space.
This is the thing Dave will say.
Yeah, the other coordinates. The other coordinates on Fisher space, they are what we call the mu's. Dot and the alpha dot and the alphas, and they are defined up to from complex scaling, from non-zero complex scaling. Right, so CP3, except not because we take a line, holomorphic line, is just, so it's a two-dimensional real, but it's a one-dimensional complex. So this is the picture you have in mind. And then we are talking Dave was division into twist actions. Again. And to write down the action, we usually use a top holomorphic one that denoted like this. So this is totally symmetric tensor coordinations. So now, right. So this, of course, has weight. These are usual coordinates on C4. So they have weight when I go down to the street. So this is actually a homomorphic form, but it has weight. It has weight 4. So it has been twisted by, this just means that it has weight 4. So it has been twisted by this sheet, by this bundle. And so that means that if I try to write down an action on the way with the big word yesterday, but it's like scalar. Then we need the scalar to have some weights because it has to soak up the weights from the holomorphic measure. So to be able for that to make sense, we take this scalar to be a bunch holomorphic one form. With a scale. So that minus 2, minus 2, minus 2, minus 4 compensates this. I have a 3, 0 form. I have a bunch holomorphic direction, and holomorphic direction divided by another holomorphic direction. This then is just a 3, 3 form, and then you can integrate it. So, over three-dimensional complex manifold. And then what we saw yesterday was also that the equation of motion in tensor space for this is that this is a holomorphic, not conform. And on space-time, this then corresponds to, well, there's a component of this field on massless scalar on space-time. Right. This is the usual magic of tensor space where holomorphic objects, holomorphic functions in tensor space corresponds to solutions of free massless equations on spacetime. The simplest example of that. And the way that another way of look about, so yesterday they just did I told you how to do the ways of seeing this from the actions. You can reduce the action on S2 to get down to, so just remind you, of course, this is also, as a real manifold, it's just R4 across S2. So R4 is R for dimensional space, and S2 is the S2 that is just fiber on top of it. So you can dimensionally reduce from that S2, and then we get back to some action on space-time. In this case, with the action space. Another way of getting that is just looking at the Fingerless transform, which is forget some of the old books on tensor theory, what you're going to see. Which now, so what's that? So the Fingerless transform, I'm going to get in the field, right? I'm going to integrate that over the S2. So there's some measure for this S2. This has weight 2, which is good because my field has weight minus 2. So this, and it's a not one form. So once I restrict it to the sphere, this is a one form I can integrate over the sphere. And I have restricted this to some particular sphere using the incidence relation. And so now, and the claim then is that this is a field on space-time. So once I integrate over the fiber, all that is left is dependence on space-time points. And this is the way to relate this, in the end, is a cohomology class in tensor space to a field on space-time. This holomorphic function of tensor space or field on space-time. And from this, you can recover also the equation of motion from the holomorphicity of the field. So this is a scalar function. You can also certainly do this. There are certainly actions that certainly representatives for all the helices of spins. So in one, we have an action, which again we use for top holomorphic form. Now I have two fields. And I think yesterday we also saw that this is nothing more than the functional holomorphic part of the curvature of a gauge bundle. And the question of this is a BF-like action, it's a holomorphic BF-like action. And the equational motion for this is telling you that this field A, which is it's a partial connection, so it's a connection that only has directions with potential holomorphic directions. There's some values in the algebra. And it's telling me that this, since the potential holomorphic part of the curvature of this connection is 0, tells me that the connection, there is a holomorphic bundle on twistor space, and by given by work, then this holomorphic bundle corresponds to self-flow solution triangles in space-time. So this is the self-flow triangles. But this action in particular, there is not only, because it's this kind of first-order action, you also have a field G. And this field G, in order for this action to make sense, this field also has to be a potential holomorphic conform. Also has values on the Lie algebra, taking the trace here to get an invariant of that. But this is twisted by -4. So this has no weight. This is the honest partial connection. While this is twisted and makes up for the weight here, so we can integrate it over.
Edward,
Yeah.
the pin is maybe starting to let you down. I don't know if it's another.
There's another one here. There are a couple of others here. Okay, I'll make this one. Also, you don't keep me on time. Yep, I'm going slower to that class. So if you dimensionally reduce this on the sphere, this action gives you get the Chalmers and Segal's action. And that's true. Gives you the Chalmers and Segal's action, which is an action on space-time. That is perhaps more familiar. It's also I can change color.
No, it's okay.
Yeah, this thing. Up to maybe some numerical factors. Right? So I do want to contract about analysis, and I did it on the wrong place. But it has to match this. So the anti-holomorphic with a chop. The anti-self-dual part of the curvature defined like this. This equation was delta at 0. So you get a self-dual solution of space-time. But you also have this other field here, and what that is doing, well, that has interpretation of being a negativistic perturbation on top of this self-dual background. And that's exactly what you get out of this. If you look at the linearized Penrose transform, just to keep matters a bit simpler. If I want to do something similar to what I did up here, restricting this field to the line, has weight -4, So I don't have enough ways to compensate. What you can do is you can add the two spinors here, compensate for that way. Then the claim is that giving me a field space-time. It gives me a subtotal field in space-time that obeys the linearized equation of motion for that application. So this action has both of them. And that's kind of the actions you'll see if you go looking at the literature. These are actions, those are the kinds of actions that you find that usually have this kind of BF character where you have kind of Lagrange multiplier imposing some constraint.
Is there a nice way to understand where that the B alpha beta comes out?
Yeah, it's a component of this guy.
Of G?
Yeah, so you remember that G, I have an S2 worth of extra fields. Because, and those, that S2 is, they said, is an auxiliary direction. And so there's no actual dynamics there. So you can either brute force it and see that there's no dynamic, integrate them out, or there's a nicer way, there's a very nice way, there's a particular gauge, which sometimes in Twitter space called a space-time gauge or Woodhouse gauge that you can pick. Remember that, sorry, one thing that it says that there's an extra gauge symmetry for these fields. So this is not only this, but there is a gauge symmetry that I can change these fields. It's equivalent to this plus the bar of some other form. Because the equation of motion is the bar of 0, so there's an extra gauge symmetry in this space, which actually makes this on-shell homology class when you get that. But the important part is that there's more gauge symmetry than space-time. So there are more gauges. There are gauges in Twitter space which are not accessible from space-time. But if you want to go to space-time, there's some particular ones you can pick. And what it does that is separate your field. It's a one form. You can separate your field about parallel fields which have direction along the S2 and along the base R4. And, and you find that on a particular gauge, there are there's some fields which you can integrate out that gives constraints, and that constraints to the fields that you're integrating over the sphere gives constraints to the fields of space-time, a particular form. And in particular, we give constraints to some form, to some components of G, which have to be quadratic, or which have to, that this component B will have to be quadratic on the lambdas, and you're going to integrate that out. So basically, what you're going to find is, theoretically speaking, you're going to find this kind of equation for some components along the S2, and that's where the B is going to come from, in essence. But I can give you some references like this, or we can do it later. So B is like a component of G that is left over, is the physical one left over after gauge fixing, and the other ones are integrated out. And if you have asked, the same thing happens more or less for A. So, going up in spin, right, integer units, and talk about spin 2. So I'm going to write the action, then I'm going to explain. There's again this top one form, which is listed by the 4. Okay. So what are these fields? So again, form of a particular weight. And this one has compensating weights. And I wrote a bracket here. What does this bracket mean? This is a Poisson bracket. But only in the new direction. So, first two functions. Oh, sorry, this is wrong. So what is this action? Okay, so what are those two fields? If you go back in the Penrose transform, then you insert those fields, what you find, you're gonna find something with 4 indices in order to compensate for these weights. Because you either have to take into account, for example, I have just the lambda children that has weight minus 6. I have weight 2, I need 4. And that's 4, weight 4 that I have to get from somewhere. You can do the same thing as we did for the D field, for the G field on the other side. Now I have something with 4 indices. So this is some kind of curvature with 4 indices, 4 scalar indices. So this is part of the Riemann curvature, or the whale curvature. The bracket? If I put it up as a okay. So the bracket is on the mu's just direction. So maybe it's going to extend out, but it's just if you remember that there's you can either see piece of space as a S2 vibration over R4, or you can see as a 2-plane fibration over S2. These 2 planes over the S2 are coordinatized by the mu's. So there's a Poisson structure on those planes, and that's the Poisson structure we're using here. And I'll come back to what is important in a second, but first, what I just want to say is that those 2 fields here, by the Penrose transform, they obey some linear equations. They're going to obey some linear equations of motion, free equation of motion on space-time, and they're going to be, moreover, in space-time they have spin 2, so that they are gravitational, linearized gravitational solutions in scalar on flat space. So you should think of them as having spin minus 2 and spin 2, so that those are the 2 velocities of the gravitons, linearized. And but what this action means, so this action has something to do with gravity. And to figure out if we get the equation of motion out of this, the equation of motion is telling me that this telling me this, but what does this equation actually mean? Well, what this equation actually means is that if I have my d-bar operator, just a regular d-bar operator, I can imagine doing a deformation of this d-bar operator mu curved operator in this way. And I can do that because this has this field has weight 2, this Poisson bracket has weight -2, so this is weightless, as you would expect this to do a regular deformation of the complex structure. And so this equation of motion is equivalent to requiring that this complex structure is integrable. And so by this is what it's called the nonlinear Grafton construction, where deformations of the complex structure, integrable deformations of the complex structure on tensor space, equivalent to self-dual ridge plus solutions on spacetime. So there's some technical assumptions that go into that, but that's the main theorem. And the reduction to spacetime is a little bit more involved, and you get an action that perhaps is not well known, but it's an action that you see that actually gives the equation that equivalent to self-duality Einstein for so ridge class self-dual solutions. Now, and the reason why we get Einstein instead of something like more general is that to get Einstein's the Einstein condition, you really need the deformation of complex structure really needs to preserve this Poisson structure on the fibers. So if you remember from yesterday at the very end, when David was asked about the W1 plus infinity algebras, he had this construction on the sphere where he had some transition functions, and those transition functions had to preserve some form on this overlap, and this is kind of the tool of that. This is basically the same thing. So this is, you need to preserve this structure, which is equivalent to preserve this Poisson bracket to get Einstein's equation. Otherwise, you could have done a general deformation of the complex structure, but if you do just a general deformation of the complex structure with some gravity differential, this in generically will give you conformal gravity. And that will come to play a role later on when I talk about twistor strings, and kind of is the reason why twistor strings generically give you conformal gravity instead of Einstein gravity. So the main point to take away is that there's ways to write actions in twistor space. They are holomorphic PF-type actions, where you usually have the two helices paired up in this way. And of course, this we can do for other spins. So there are actions for fermions that you can do in this way too. They're also holomorphic, also have to do with just the Penrose transform, giving you they have different weights, and those weights correspond to different helices on space-time. And if you dig a bit deeper, a little bit deeper, you can also find a spin very well knows how you spin action for higher spin fashion. I won't get into details on that. Okay. So to be Einstein, you have to preserve this Poisson structure on the fibers, on the mules. So, which is in some sense, the mules are in some sense what becomes the space-time directions after you integrate out the aspect. So you need a particular deformation of the complex structure, integral deformation of the complex structure to get Einstein. Otherwise, you just get self-dual viable. So just not fun. so now for the second part, I want to talk about quantizing, quantization of these actions, and their origin in terms of some kind of string theory or kinds of string theories. Yeah, okay. So, quantization. So, generically, these actions, Cairo actions are played by anomalies. Those are no exception. And what I find is that the anomalies for these actions, anomalies of the extra gauge symmetry, are given by the one loop amplitudes without positive velocity, both for the gravity and the gauge sector. Right. So these are not anomalous in spacetime. Right? Those, if you're just taking a spacetime four-dimensional point of view, those are just amplitudes as a theory. But because we have this extra gauge symmetry that can depend on this S2 on twistor space, then you have to take into account this extra, that this symmetry is still gauged when you go into the quantum regime, and these anomalies. So that will mean that these amplitudes have to be zero, but they are generically not zero. So they are obstructions for the existence of the quantum theory in general. And so there's a couple ways where you can get consistent quantum theories. The usual way, or the way we've been doing the amplitude and the original twisted string, is just to add SUSY, because with any amount of supersymmetry, you find that the fermionic and bosonic contributions to amplitude cancel, and you get a zero amplitude. That works both for EMUs and for gravity, even with n equals 1 supersymmetry, all plus amplitudes vanish. And more recently, we saw in this work by Kevin, and then Kevin for EMUs, and now David and collaborators for the gravitational sector, that you can add some extra degrees of freedom. In this case, it's a scalar in space-time. It's a bit more complicated what it is in twistor space. And then those amplitudes are going to vanish, but the mechanism is slightly different. This is there's a Green-Schwarz cancellation. There's a mechanism, which is a Green-Schwarz mechanism, that cancels this anomaly. And it works in the same way as the usual, when you think the usual Green-Schwarz is that you have some loop amplitude that is just from the gauge sector, and that gets cancelled by some free-level contribution where you exchange some kind of gravitational degree of freedom in the middle. It's just that this gravitational degree of freedom, in this case, is a scalar. So you can think about like a gigaton, but it's the bit of 20 joule on space. So I'll start talking. I'll try to divide the next couple minutes for the talk into talking a little bit about this way of doing things. So this is related to the old twistor string. So I'm talking a little bit about these old twistor strings, and then again I'm going to talk a little bit about how this is achieved and what this kind of theories do. So this now is an old story. The original twistor string by Witten is from 2003. And I'm sure it's well known for a lot of people. There's also a lot of young people that might not have seen it. comment a little bit about that. And there's also correlation with Berkowitz, which is slightly different, that I can talk about. Witten Berkowitz. So, as I said before, the idea on tensor space that you have holomorphic objects corresponding to equational motion in space-time. So you might imagine that if you want a string theory on tensor space to give you something sensible on space-time, or something that you understand on space-time, you want the equational motion for the string to be holomorphistic equations. And there is a string theory that does that for you. There's several, but there's one particular, is a topological string. So if you take the topological B model, all I need to know for the purposes of this review is that the topological B model is a string theory, which is topological. So means that it doesn't have all of the massive degrees of freedom, it has only a small set of degrees of freedom, it doesn't depend on the metric, on the target space. And moreover, it's very important for physical string states to be Q-closed. And in this model, Q-closeness is basically equivalent to be D-bar closed. So you get holomorphic objects. So the Q cohomology is, in a sense, the double cohomology on target space, at least part of the double cohomology. And so that was the motivation of Witten of studying, one of the motivations to study the topological B model on tensor space, because then the string vertex operator, the string states, are going to be, the physical ones are going to be D-bar closed, so they have a chance of being something on space-time. But one issue that you run up immediately is that in order to cancel anomalies, you need that the target space to be Calabi-Yau. So what that means, it means that there must be a top holomorphic form. So let me say that the target space, call it M, it's Calabi-Yau. So you need to have a global, everywhere defined, holomorphic form. That's actually the non-trivial requirement on a complex manifold. And it's something that the tensor space doesn't obey. Because when you wrote down this form that we have been using to construct our actions, it is a holomorphic reform, but it's twisted by a quad, so it has weight. So it's not Calabi-Yau. So you don't cancel the B model is anomalous, so you can't in fact just straight away write the topological string on physics space. So Witten's idea was, let's supplement. Yeah. So in a boundary?
It's a boundary, right? It's a non-compact space. Right?
Yeah, but if you make it, you can make it Calabi-Yau by removing points on the sphere. On the sphere. Sorry?
You already removed enough points for that, didn't you?
To be non-compact, yes. But there's still, you can make it Calabi-Yau by asking a form to have poles at the boundary, if you want.
That's kind of what Kevin does.
That's what they do.
It's that idea.
That's that idea.
That wasn't the idea.
Yeah. So the second point is kind of like that. There's an idea of you can there's another you could get a form with poles holomorphic trifold has poles, but your fields have zeros. So you add some extra boundary conditions such that the whole integrand is well defined, and then you can write something like that. But that is the level of the field theory. Perfect. At the level, I don't know if you can get away with that at the level of the topological V model. Maybe you can, probably can. Probably should write the paper. But yeah, that's kind of Kevin's idea. But Witten's idea was to add some fermions, some fermionic coordinates, fermionic, and I add 4 of them. Moreover, they all have weight 1. So I asked them to have values on this O1 bundle, so they have weight 1. Minus 1. So now I write a form which is Berezinian, which is the analog of a top form on a superspace. No. Let me write it. So the fermions have weight 1, but I want the fermionic integral to be well defined. So for the fermionic, so for this to be 1 and be well defined, then if the fermions have weight 1, the form part of the fermion has to have weight minus 1. So these guys have weight minus 1. And now the whole object has weight 0. So this whole thing here has weight 0. And so I can define an extended space, which is the original Twistor space, but I join 4 fermionic coordinates, and I call that the super Twistor space. And as a super manifold, it is Calabi-Yau, super Calabi-Yau. So Witten's idea was to write down a topological string in that extended space. And then by analogy, you can extract the effective theory. So the low energy action for the string of the string action for this. So now this is usually denoted as significant by 4. And in the open string sector of the topological string, we'll know that for the V model, the effective action you get is a holomorphic Chern-Simons action. So this is an analogy. If you had an actual Calabi-Yau manifold, what you will get is the usual 3 form times holomorphic Chern-Simons, but now in the super Twistor space you get a fermionic component for this 3 form, and also you get a super field. So now these are fields on the Calabi-Yau on the superspace. So it depends on the fermionic coordinates. So you can expand in terms of the bosonic components. when you do that, you find a whole multiplet of fields. And just schematically fine. That's a whole multiplet of fields. This is a whole matrix sum, so this should be taken as a connection without any weights. You don't need any weights because it's already weightless. So the top component here is a holomorphic one form without any weight. So it's a connection. So this is like the positivistic graph that we had in the action before. Then every time I add a third one, I have to compensate with the weights of those fields. So this, for example, has weights -2, so those are scalars. But all the way down, we have weights -4, which is negativistic rule. All in one super multiplet. Of course, if you integrate out the fermionic directions, you are going to recover the action we had before for the self-Lorentzian use plus all of the SUSY columns of this. So while this is a holomorphic check summons, which is more usual thing from top left to screen, what we got effectively once we integrate out the fermionic directions, we got back to the actions we were talking before. Right? But what you do get out of this construction is a set of actions that altogether are anomaly free, so you can quantize them, because those end up being supersymmetric, and this actually ends up being n equals 4 supersymmetric, and this is the whole multiplet, perturbative multiplet for n equals 4. So here. So this is a description for n equals 4 self-Lorentzian use. The whole super multiplet. And after that, then you can compute amplitudes. Of course, this by itself has no amplitudes. It's self-rule has only a 3-point amplitude depending on signature. But what you can consider is some, we never call maybe some gains on some corrections, but really they're in this way they are probably better explained by using the Williams-Berkowitz description of this. We have slightly different description of the worksheet theory, but you find that you can compute amplitudes on this. On this theory, and these amplitudes have a form where the MHV amplitudes are supported on lines on twistor space, and MHV amplitudes are supported on degree 2 vertical twistor space, and to the KMHV are supported on degree k+1 on twistor space. So this is the support of the amplitudes after the, so basically the amplitudes are supported on higher dimensional submanifolds on twistor space, and that's given by the string. But basically one of the motivations to find a twistor string was because we can, as it explains in the beginning of this paper, is that the amplitudes, the gauge amplitudes, have this kind of a nice interpretation on twistor space as being supported on higher degree curves. But this is the gauge factor. Oh, until when? When do I have to stop? So this is the gauge sector, but string theory famously also has gravity. Cannot avoid that. in the gravitational part of the topological B model, it's something that you might like because, so it's the closed string sector, if you will. It's related to deformations of complex structure. But there's no really constraints on this deformation of the complex structure. So what you end up is that the closed string sector gives something like gravity because it deforms the structure of crystal space. So it relates to some kind of gravity in space-time, but it gives you conformal gravity. So that's why you expect that just a regular topological string that just deforms the complex structure in any way in tensor space is going to give you some gravity, but it's going to give you a conformal gravity. Because in tensor space, there's this extra structure given by that Poisson bracket that needs to be preserved if you want to get Ricci, to get Einstein equations all the time. So if you're just interested, I mean, it still can be an interesting theory, even though you have higher derivative excitations. But it's in principle anomaly free, and you have a string theory description on this super space. If you want to get gravity, maybe, then you have to look at Dave's paper from 2013, where he wrote down a tensor string. That's an n equals 8 supergravity tensor string. Where now I have 8 fermionic directions, so I have a big. Now this has weight, but that's compensated by some superfield H that now has all of the degrees of freedom with the perpetuative excitation of n equals 8 supergravity. So the effective answer will be something like this. But it's something that is much closer to the Witten-Berkowitz string in the sense that this is, if you know a little bit about their case, this is given in terms of a constrained beta gamma system. So this is like the Witten-Berkowitz string, and actually like the pure spinor string of Berkowitz. And for those in the know a little bit of pure spinors, one of the nice things about having this kind of string theory is given in terms of beta gamma constrained beta gamma systems is that you can make supersymmetry manifest, but the computation of amplitudes requires a bit more care in order to define them. So there's things which need to be understood more properly, both from the worksheet and the Italian space. But nonetheless, there is a construction containing gravity on the worksheet that does give you amplitudes these are amplitudes in the n equals h supergravity for all of them. And in analogy, very similar to Young-Mills, n equals 4, amplitudes are supported on lines on tensor space Paranormalidad is supported on the neighborhood of lines. So they extend a little bit along the normal direction, the normal bundle on this. But they are still have the same grading as the youngest one. So they are still supported on the neighborhood of these manifolds on this space, the subspace on this space. So why is this interesting? So recently there's talk about chiral algebras and how chiral algebras appear on this space. On this work by Kevin and Natalie. And you also see the same structural chiral algebras in the celestial OPEs. And these constructions already have chiral algebras in them from the very beginning, and in particular, which is very clear if you look at the image receptor. So if I tell you a little bit, don't have time, so because I want to get to the end of the talk a little bit about the other work. So I'm just going to tell you a little bit, and you can ask me later, or ask him, or ask me, or explain. So that these twistor strings, in general, they have this chiral, they have this representation, they have this worksheet actions in terms of beta gamma systems. Beta gamma systems should be the chiral should be CFTs, so they give you chiral algebras, constrained beta gamma systems, which means that they are not only free, there's some constraint you have to impose on them. And so, but there are chiral algebras on the worksheet. So there's some chiral algebra on the worksheet. But as I told you that in the image receptor, this worksheet gets mapped, in a sense, to lines. So if you're only thinking about the image receptor, amplitudes are supported on lines. So you can make an identification of the chiral algebras on the worksheet and with chiral algebras in the target space. And you can give a representation for some of these in the target space by using the worksheet, by using the identification. This is roughly the idea that Jim and I, Anato and Wei had when we were doing this OPs from the subsector. But it was already here, this idea was already floating around for the twistor strings, for both for the gauge and also for the gravity, at least for the image receptor. And in particular, you can also write them based in the same one. The other way was talking yesterday is that you could just start from a target space and you try to find there is this conformal blocks that he was talking yesterday, and if you just try to follow those, get the simplest description of this conformal blocks, you end up reproducing some parts of this chiral algebra from the twistor string. So you can see that at least in this, you can take them as basically to be the origin or some other description. The twistor strings give me another description of this chiral algebras, at least for the image receptor. And before I move on to the last part, I just want to say that this all has been done in 4 dimensions, but you can have higher dimensions actions and higher dimensions string theories, twistor string theories. And there are several ways of doing that. And they are really relying on something called twistor strings, twistor space, and twistor strings, which I'm happy to talk about in person more if I'm interested, but there are some things you can do in higher dimensions. It's less clear if there's some kind of topological string behind them, but you can certainly talk about this kind of models with chiral algebras in higher dimensions. Questions? So, to finish off, then I'm going to talk a bit about the other way that you can get well-defined quantum theories on Twitter space, or the holomorphic quantum theories on Twitter space, which is what has been done by Kevin and later Kevin Paquette and now Atto, which is again, so again inspired by the topological string, again inspired by the topological B model. If you just have an actual Calabi-Yau manifold, and you have a honest holomorphic form, top holomorphic form, close to fine, the action that you find, the effective action for that string, as I said before, is a holomorphic Chern-Simons action. But this is anomalous in general extent. So there's an extra piece that comes from the gravitational sector. With this eta field. What this eta is, in this case, is a not one form on n with values in the closed two forms. And then what happens is that this gives you some, you can think about anomaly as a one-loop amplitude, or plus amplitude, the anomaly. And there's a three-level amplitude where you exchange this eta field that cancels that. So this comes from the gravitational sector, so you have a Green-Schwarz mechanism to cancel that anomaly. That's what usually happens in topological string. And this comes from the gravitational sector because you can using the top holomorphic form, there's a map between some forms, polyforms on a direct space, where this is you can see that there's a map between the Holography differentials and this field. So basically, the tree form eats one of the tangent indexes and leaves you with a holomorphic two indices. But it's very important that you need a Calabi-Yau condition in order to have this map. So that's an Holography differential generates the formations of a complex structure, which, as I told you before, is part of the gravitational sector of the topological string. And so that's why it has this flavor of being a Green-Schwarz mechanism, because it looks like the Green-Schwarz mechanism for the usual string, where you have gravitational degrees of freedom killing a gauge number. Right, so that's what we get. And so what Kevin, inspired by this, what Kevin had in crystal space, we don't have the holomorphic, we don't have the Chern-Simons actions, we have the BF kind of actions. Again, engage the type of seeing ranking this action. At this action. And the idea was to let me paste into the same thing. I add some degrees of freedom. Some connection that is weird, not important right now. I add some extra degrees of freedom, which is eta. When the values in the same bundles of those forms. And now what he showed is that with some particular coupling, that depends on the gauge group, you can, for certain gauge groups, you can kill that anomaly. And moreover, they and collaborators showed recently that if you extend this to gravity, with some other, you can go to the same degree of freedom, and the S is related to the aging in a way you can tell. S is a connection on the connection derived from the gravitational degrees of freedom. But in any way, at the focus of the gravitational degrees of freedom, and with some proper choices of A and B, what they and collaborators showed is that you don't only kill the gauge anomaly, you kill the gravitational anomaly, and you kill the mixed anomaly. So that's another way, inspired from the topological B model. A way to do this without using supersymmetry is by adding this extra degree of freedom. But on tensor space,
So this looks like it at this.
well, Costello, this is really Costello.
Costello, okay, sorry. At this
term, yes.
And that's going to make the gauge theory work.
Yeah.
And then
they because they show that the same field, but with this kind of coupling and with a particular choice is enough to make curvature. S is some connection derived. It has SL2 connection derived from the gauge, the gravitational. So yeah, but no, so there's no supersymmetry. But it's also inspired with the topological B model, but the identification of this field with some autonomy differential is spoiled because we don't have this. If you're trying to do a mapping like that between forms, you're going to twist by your 4 everywhere, so you don't end up with an honest autonomy differential. So, but still, it's something that even though we don't have a complete derivation of this form from theory yet, and that's an open question, for sure. It's something that just works, and you can work with that.
and what's the gauge group?
What's the gauge groups?
Yeah.
That's what we need to.
SOA.
From sectional.
Just the trace of the fundamental two generators also
Yeah, it's the same thing for the usual bridge knots where there's a single trace from the gravitational path that has to be cancelled by something that is double trace because we're exchanging something that's polar. So you need to have that. So there's some particular rules. So how much time do I have?
5. Yeah.
Okay,
Well,
great.
7 minutes.
So maybe I'll rush a little bit, but we can talk more later on. So in one of the papers, maybe I can talk about this. All the paper, we can talk about the newer things they did. How do they get arrow algebras, for example, out of it? So this is Kevin and Natalie. So this for the graph. They go for both sectors, but here they did for the gravity just believing that there was a way of making it work, and then they show that there is. Where you can take our usual PF action. Now we're working on just the bosonic tensor space before. And now you think about doing dimensional reductions. Doing dimensional reduction on S2, so reducing on S2, gives me a four-dimensional theory. Moreover, it's a four-dimensional conformal theory. Right. So if you look at it, so there's a Hilbert space for this four-dimensional theory on S3 that you can get, and you can get from the six-dimensional theory by doing a dimensional reduction on S2. And you don't lose any degrees of freedom because S2, once you cure all the anomalies, then S2 is truly auxiliary. But here you pull it on another way, and you can think about doing the reduction on S3 and keeping the KK modes. If you do that, then the gauge action becomes an action in three real dimensions, which looks what is an action in three real dimensions. Which looks like some PF kind of action again, with some extra fields, plus decay, modes. In this kind of actions, they turn out to be mixed topological holomorphic theories, what that means. It's a theory that is topological along the R direction and holomorphic on S2. So you've done a particular dimensional reduction along the S3 where you've kept the holomorphicity along S2, but the direction, the leftover direction, the radial direction if you want, is topological. So local operators are the ones that are topological when you translate along the direction, but holomorphic when you translate along the S2. And those are theories that they appear in some listings of two-dimensional supersymmetric theories, so there's some literature on that. And in particular, there's some literature on that that tells you, first, is that in this kind of holomorphic topological theories, that there exists chiral algebras that live on S2. So they are boundary chiral algebras. And moreover, the Hilbert space without the KK modes for this three-dimensional theory, so it's a Hilbert space on S2, is given by the conformal blocks of the chiral algebra. So kind of similar in analogy to Simon function. This three-dimensional topological holomorphic theory. Now you have a Hilbert space which is given by conformal blocks. Now the chiral algebra, and by that I mean conformal block is any function, linear function on this algebra, the elements of this algebra, that just gives you some number. With some properties. So, I know it's very tempting to think about it this way, yes. We can talk later when I'm not being filmed. In principle, no. In principle has nothing to do, but maybe there is a relationship. It smells a little bit. So, of course, there's a whole literature on this. There's quite a lot of actions and parallels you can get of that, but what Natalie and Evan showed is that first, the chiral algebra that you get by doing this with a twistor string with that action, and also the gravitational action, you could recover the S algebra in the gauge sector, and you recover the loop algebra of the wedge, the 1 equals infinity, in the gravitational sector. you do need to keep all the KK modes to have all this algebra. Moreover, you get this algebra plus some enhancement by the negativity, plus some matter cubes that comes from doing the dimensional reduction of this guy. And that's important for quantum consistency. And the same thing here, you get some enhancement by the negative realistic guys plus some matter is in the gravitational sector. So that's how they recover the algebras. And moreover, because these Hilbert spaces are the same, and that's there for each of the dualities, that space. This is a Hilbert space of conformal theory, so you can think about the space of local operators by the operator state correspondence, and that's the same as the space of conformal laws for those chiral So that's one way of that it gets. We cover some of the celestial algebras out of this, and it's different, slightly different procedure, different thing than the twistor strings, but it's not symmetric and invokes some other part of the literature. But of course, but this was not now. Just to finish off, I'm just going to say it in words that this is inspired by string theory, but there is still no topological string top-down construction of this. And if you want something like that, I think Athol, Natalie, and Kevin gave a construction. But then what they do is to get a Calabi-Yau manifold, they have a homomorphic tree-form with some poles, and they require some particular boundary conditions on the gauge fields to define a theory. And that's the latest paper where they have this duality between some chiral algebras in 2D and going to space. And that really comes from string theory. That's really a topological string description of that. And of course, because of topological string, you also end up with a gauge sector coupled to conformal gravity sector. So I think to summarize, to finish up this part, there's a few different constructions we can do. Some of them we know what to do from string theory, but they might not have all the properties we like. Some of them are more twistorial, but they also have some weird properties, or they have to be careful about how to find some of these. But I think there's still quite a lot to be understood from how to construct this, even just a sub-rule separate from topological strings. There are other topological strings that depend on the Kähler structure. Maybe this has something to do more about the Kähler structure, and that's what we should be looking at. And another big question is if you can move up beyond the MHV sector, right? So this is kind of, there's no MHV gradient here, but everything here is on a sphere. So it's on a line on twistor space, and in the original twistor strings, the lines kind of, you can think about the line as being the MHV sector. The original twistor string also knew how to go beyond the MHV sector. It's more complicated. You still have some parameters, but the relationship space-time is more complicated. Goes through scattering equations. There's some stuff later on. And it would be interesting to see if there's something like that here where you don't have to talk about higher degree curves, other instant functions, other non-perturbation brains on topological strings. So I'll finish here.
Any question? Yes.
What's the current state? Maybe. The thing is, yeah, you want to hook up something. First, you want to see that there's an anomaly on these actions, which you might expect because there's not the platonic quantity instead of output. And then you might want to do something like that.
Space. Is there any anomaly to And the tester space, non-chiral.
No, but the action will be,
So then, the one more number. But
well, it's non-chiral in the sense, but you never write down anything like E operator, right? It's always that and that. Don't do that. I don't know, okay, so for the dimension of the crystal is to chiral. I don't know what actions you use in a high dimension.
what do you mean by it's so true?
When you write down W and that, but then it's still divide. The things that are still holomorphic, I don't know, this is maybe
Of course, it's still holomorphic. I just mean it doesn't care any more about the 1 plus n than it cares about the 60 plus.
right. But I think, and also, yeah, when you go to the state, holomorphicity is just not allowed to be extra.
Yeah.
Anybody else? Any question? Guess we can discuss later. Okay, thank you very much.